Hello there. In this video we're going to answer the basic question, what is a logarithm? So if you have never heard of a logarithm, then this video is definitely for you. Or if you have heard of the word but you don't exactly know what it is, but you have seen it used, say, in your math class or in some paper or whatever, then this video is definitely for you as well. So the only thing that you need to know are the basics of exponential functions and some of the basic ideas of inverses. Alright, so let's begin by reviewing the basics of exponential functions. So exponential functions. Let's do a quick review. So an exponential function is one of the form f of x is equal to a to the power of x, where a is some number bigger than 1, and there are some properties associated to this function f. The first example, or the first property, the domain of an exponential function is the set of all real numbers, and the range of this particular exponential function is going to be 0 to infinity. The second property is that it has a horizontal asymptote at y is equal to 0. It does not have any vertical asymptotes. F of 0 is equal to 1. And one of the properties that we proved for exponential functions is that f is strictly increasing. So if f is strictly increasing, then this also implies that f is 1 to 1. So if a function is 1 to 1, that means f is invertible, which means that f inverse exists. So if f inverse exists, then you can actually say a lot about this function f inverse just by these properties. So let's talk about this function f inverse a little bit. So let's take a look at the graph of our exponential function. So this is going to be f. Let's assume that this is the x-axis and this is the y-axis. So the line of symmetry is this line, y is equal to x. So we know that f is invertible, it passed the horizontal line test clearly. That means it has an inverse and it's somewhere over here, right? So this is going to be f inverse. So we know what the graph of f inverse looks like. So let's just list some of the properties of this function. Even though we don't exactly know the algebraic representation of it, we know some properties of it. So the first, the domain of the inverse is going to be equal to the range of the original, and the range of the original was 0 to infinity. And the range of the inverse is going to be the domain of the original, which is going to be r. From the graph, you should be able to see that that is true. Instead of a horizontal asymptote like its original, it will have a vertical asymptote at x equals 0. You can pretty much see that here, same as this was a horizontal asymptote for the green curve. If f of 0 is equal to 1, then that means f inverse of 1 is going to be equal to 0. So that's going to give us a point on this curve. So this is 1, 0, because this point here is 0, 1. And also it's very easy to prove that if f is increasing, its inverse image is also strictly increasing. So it's not decreasing. It's not the opposite of what's going on here. All right, cool. So we know pretty much everything about this function, so it's useful to give this function a name. So this inverse function, f inverse of x, we're going to denote it, so denoted by log with an a on the bottom, x, right? So this function is called a logarithmic function. So what is the logarithmic function? It is the inverse of an exponential. Now there is an alternative definition for logarithms using integrals if you're familiar with integral calculus, but we'll leave that until another day to discuss. Alright, so we denote it by this name and we denote it as so. So the function f of x is equal to a to the power of x. So remember, a is just a number, and if you change the base of this exponential function, remember this is called the base of the exponential function. This also is called the base of the logarithmic function. If you change a, then both of these curves will sort of stretch out a little bit. Alright, so let's just go through some basic examples of logarithmic functions just using these things that we've already discussed so far. So we're going to define f of x to be equal to 3 to the power of x. And we should be able to calculate a few points of this curve. For example, f of 1 is going to be equal to 3, f of 2 is going to be equal to 9, f of 0 is going to be equal to 1, f of negative 1 is going to be equal to 1/3, and f of negative 2 is going to be equal to 1/9. So if f of x is equal to 3 to the x, of course it has an inverse. So this means that the inverse of this function is going to be log base 3 of x. So now we're just going to reverse the domain and range. So this means all of these is going to imply that the log base 3 of 3 is equal to 1. The log base 3 of 9 is equal to 2. The log base 3 of 1 is equal to 0. The log base 3 of 1/3 is going to be equal to negative 1. And the log base 3 of 1 over 9 is equal to minus 2. And that's just using the property that the domain of the original is equal to the range of its inverse, and also vice versa, right? Now, it's possible to sort of interpret these without thinking directly from the exponential form. For example, if we have something such as the log base 2 of 32, and we want to know what this is equal to. So this is equivalent to the exponential form, so 2 is the base of the logarithm. That means this corresponds to a base 2 for the exponential. X is going to be the exponent, and this is going to be equal to 32. So remember, the domain switches with the range between inverses, right? So this question asks 2 to what power? So 2 to what power gives us 32? So this question applies to both of these expressions because both of these are equivalent, and this is a basic example, so of course we know that x is going to be equal to 5. Now how can we algebraically get this answer a little bit more swiftly? Well, there is a way. So if we have log base 2 of 32, the goal is to rewrite 32 with this base. So this is going to be equal to the log base 2 of 2 to the power of what? So that's going to be 2 to the power of 5, and that's just going to be equal to 5. So in a way, this log base 2 and this 2 of the exponential are going to cancel, just leaving us with this number 5. So that's almost like the algebraic way of dealing with it. So let's use this approach to evaluate a few logarithms. So the first example, suppose we have log base 16 of the power of 4. So 16 to what power gives us 4? Well, 4 is smaller than 16, so the power cannot be bigger than 1. So how is 4 related to 16? Well, 16 is the same as the square root. The square root of 16 is the same as 4. So we can rewrite log base 16 of 16 to the power of 1/2. So again, this cancels, and we're just left with 1/2. So the log base 16 of 4 is 0.5. Another example, suppose we have the log base 4 of 1 over 16. So we can rewrite 1 over 16 using negative exponents. So that's the first thing you would do for this. So we have log base 4 of 16 to the power of negative 1. And how can we write 16 with a base of 4? So that should be pretty simple. So that's the same as log base 4 of 4 to the power of 2, which is raised to the power of negative 1. And then we can multiply those exponents directly, right? So we have log base 4 of 4 to the minus 2. So that means 4 to the minus 2 is the same as 1 over 16. We have our base of the logarithm and base of the exponential the same, so they cancel, just leaving us with the exponent, minus 2. And let's do another example. So example 3. Suppose we have log base 5 of the cube root of 25. Alright, so firstly, the cube root is the same as the 1/3 power, so let's just start off by doing that. So we have 25 to the power of 1/3. And how can I rewrite 25 with a base of 5? So we know that's the same as 5 squared, right? So we have 5 squared to the power of 1/3. We have a power to a power, so we can multiply that directly. So this is going to be equal to log base 5 of 5 to the power of 2/3. Now we have our base of the logarithm and exponential equal, so they cancel. So this is just going to be equal to 2/3. Alright, so that's just a basic introduction and an answer to the question, what is a logarithm? Definitely there are more things to be said about logarithmic functions, for example, their properties and their applications as well, which we'll discuss in the upcoming videos. Hope you enjoyed.